take on any value in an interval. So this is actually coming back from chapter 2, but it's also in your book on page 230. And this was the problem about particulate emissions. If you remember that problem, but again, it's on 230, but back in chapter 2, they're talking about how to make histograms. And so they figured out what kind of pollution was being produced by a sample of 65 cars, and they came up with this, right? And they said these are the emissions down here, and this is the proportion for each of the cars. So that is a continuous variable. But now what happens is, chapter 6, we start getting into a little bit theory, not a lot of theory, but a little bit. Because what happens, instead of if I just took 65 cars, let's say I took 1,000 cars. Instead of having 7 different bars or 7 different classes, I might want to have 10 or 15, right? And let's say I take every car in the world, which is quite a few. And if I want to set up the little bars, it wouldn't look like this, right? You would have so many little bars, it would start looking like a smooth curve. And that's what the picture on page 230 is representing. Here I just had 65 cars. That's a sample. What happened if I took every car in the world and laid it out? It would end up looking like a smooth curve. And I'm assuming in your class before you talked about this, right? 'Cause you talked about when curves were skewed right, skewed left, symmetric. So you look at this, and even though it doesn't have a curve to it, you go, well, it kind of looks like this. So it looks like it's skewed right. Now you don't have to imagine the curve. The curve is actually part of the problem. So in this section, we're going to be talking about 2 different things. One is populations, not sample. And 2, this is again going to be continuous variables. So last section, we were talking about discrete variables and samples, not population. These ran so many trials. So in our notes, let me look at that. I did not see this. Make sure it's better, just make sure. I don't see it, so if we come across it later, we'll talk about it later. So when you look under a curve like this, if this curve encompasses the whole population, this is what is called a probability density curve. And again, a little bit different name. But it's still a curve that represents whatever it is you're measuring. And again, this is your x values, whatever they are, and this is your y values or your frequencies, relative frequencies. Now, on these, in this section, and actually in chapter 6, if you look at this entire curve, and you can put this on your second page, I think it's your second page, the one that says for continuous, the first 2 words. The area under the curve equals 1. Always. And if you think about it, that's really not different than what we did before, and I should erase my first histogram over here. Because when you do a relative frequency histogram, and you add up all the bars, that equals 1. Same idea here. I just don't have any bars because I have so many of them, I don't want to add them all up. So the area under this curve is always going to be considered to be 1. Now, on the middle of your page there, two important things. When you talk about the area under a curve, if I pick any two values, right, what we're going to do in this section is we're going to learn how to find a certain area, or proportion of an area. So, an area under a curve has two representations depending on the problem. So that's what she has on here already, is one, it's the proportion of values between A and B. So that's what the first one is. So the proportion of population, which proportion is basically your percentage, right? So how much of your population is in here? Is it 20, 30, 40? And that, we're going to learn how to calculate that in a couple minutes. And the second thing this could mean is what's the probability of a random value being between A and B. So, again, if you could take and put in the population, all the values in a hat, and you draw one out at random, the area under the curve here, between these 2 points, it's whether it's 10 and 20, 50, 100, whatever, that tells you either the proportion of the numbers that are there or the probability. Now, I think this makes more sense once we start working through some problems. Like I said, this gets a little bit more theory, but it's not bad. It's not. So if you look at the next example, and again, she's looking back at page 230. It says, suppose the area under the curve between 3 and 4 is 0.18. So I shouldn't have erased my picture here. But again, it's the same idea, but we just don't have a histogram. So I'm not going to redraw that whole histogram. So you use your imagination here. All right, so this goes out to 7, but if the value here was 0.18, right, it just says the proportion of cars who had their emissions between 3 and 4, whatever it was, particles per million, was 0.18. That's the same thing as the area, or the proportion of the area under that curve. So now what we're going to do, again, is look at curves like this, and you're going to be able to figure out how much of an area is underneath that piece of a curve. Like I said, it'll make more sense when we actually plug in numbers into these things. So that's going to be the goal here. Come up with these. Now, before we get to that, we get to go back to our curve. So if I have a curve that looks like this, that looks relatively symmetrical, right? So we'll pretend it's symmetrical. So another term for symmetrical that's more math related is called normal. So this is called a normal distribution. So when you have all your data in a symmetrical, it's normal, it's said to have a normal distribution. The reason that's important, and you've talked before, right? You have skewed left, skewed right, and normal. For the statistics to work later on in some of the problems, the assumption behind the scenes is going to be that it has the population has a normal distribution. So you're going to see that all the time in the assumptions. So just think in your mind, when you hear the word normal, you think of a symmetry. Now, on a normal or symmetric curve, right in the middle, remember, is our mean. And you can go left to the right, and that's your standard deviation, your measure of dispersion. So I can go to the right, sigma. I can go to the left, sigma. Now, do you remember, between one standard deviation, how much of your data is in between one standard deviation left and right? 68%, remember that? And all you do is a decimal. And then if I go out another standard deviation, so if I go out 2 standard deviations, close. It's about 95. I remember, I always forget, I think it's like 95.43 or something like that. So it's about 95. And then if you go out 3, you get almost all, right? Because you get 99.73%, you get almost all of it. So any normal curve will have these characteristics. Again, just a little refresher for terminology. What's the rule that this follows? It's over there, E. Empirical rule. Empirical rule. So anytime you have a normal curve, that normal curve, the mean will be in the middle. You can go out 1 standard deviation each way, you get about 68% of your data. Go out 2, it's about 95, 3 is about all of it. Now, depending on what you're collecting your data on, the means don't have to match each other, the standard deviations don't have to match each other. And she actually has, that's the next page, never mind, we'll wait till we get there. They don't have to match, but they will all have a similar shape. Another fun thing here. I always have to look back with her note, but she's gonna put that in. So one thing we're going to do, rather than have a lot of different curves with different means and standard deviations, we're gonna look at a specific normal curve that has a mean of 0 and a standard deviation of 1. So just remember, a normal curve, just a nice little bell-shaped curve, can have any mean, any standard deviation. But if you want it to be with a mean of 0 and a standard deviation of 1, that is what's called a standard normal curve. And that's what she has on your notes. So your mean is mu still, your standard deviation is sigma. Then right in the middle, it says a standard normal distribution has a mean 0 and a standard deviation of 1. We're going to talk in a minute, but do you remember back in the last chapter calculating something called a z-score? That kind of sound familiar? We'll talk about that more, but that's going to be key going forward on these things. So a normal curve is just one that's bell-shaped, symmetric, with a mean and standard deviation. But now we're going to compare these here. So look on the next page. Because here she has a picture. I think this is your next page. She has examples of normal curves. I hope. So you can, again, you can draw any normal curve. One thing I do want to show you is your mean is in the middle for just a normal curve. And normal curve, they're actually going back, there was three things we measured for center. Mean, median, and mode, remember that? On a normal curve, the mean equals the median equals the mode. So all three of those are going to be the same if you have a normal curve. And one more thing on this page, so you can put this on that page to kind of help you. Because it's symmetric, if I looked at the left half of this, what proportion of my area is going to be to the left of the mean? Half. And I'm gonna have half to the right. And remember that, because we're gonna use that information in a little bit. So, kind of a lot of arm waving so far. Normal curve is symmetric. It can have any mean, standard deviation, but it's going to match the empirical rule. And this is gonna be important later, because again, as you do certain problems, you have to have a normal distribution. So make sure I'm still in order. You have a page that says, we will use the calculator to find it. Okay, so guess what? We're going to use the calculator. So instead, remember, of using any normal curve, if I use a standard normal, just remember your mean is 0, and your z-score tells you how many standard deviations you are above. Okay? So if I go one standard deviation over here and one standard deviation here, my z-score is 1, -1, and I still have 68%. So that's a standard normal. And if you do standard normal, it just makes the math easier, because everybody's looks the same. So now we're going to use our calculators to find the area. So I'm going to take a different example, and then we'll go to the one she has. So on the page, where she said, we're going to use a calculator. So I'm going to give you an example, and we're going to use a calculator to find it. So let's say I give you a standard normal curve, and I say I want to find the area to the left of z equals 1.3. So I want to find the area under the curve to the left of 1.3. Again, what is the area under the whole curve? 100% or 1. So, z tells you how many standard deviations I am away. Z is positive, so I go to the right. So my z-score would be someplace over here. That make sense? I want to find the area under the curve.
Wouldn't it just be 68%? Or 0.68?
So the area would only be 0.68 if I go between 1 and -1.
Okay.
That would be 68. But if I give you any other z-score, because what that 1.3 says is I'm 1.3 standard deviations above. Keep that in mind. So think about this. Now again, in my class, what I require them to do on problems that have like z-scores, I make them draw a little picture. So you can look at the picture. Because when you come up with an answer, you know that half of the curve has to have what percent of the area? Or what proportion? Half. So isn't this going to be a lot more than half? So if you plug it as a calculator and you get a 0.2 or 0.4, you did something wrong. Now, the other fun thing about this, I said it gets kind of a little bit mathy theoretical. This curve goes on forever. Do you remember from college algebra days, asymptotes? So this curve really goes, no one ever visits those again. This kind of goes on forever. You think of it going on forever. In your calculators, if you go all the way to the left, we go to negative infinity, right? Well, we don't have an infinity button in here. So what we do normally, if I'm gonna go to the left, is I say my left bound, I wanna go all the way to 1e to the 99. Do you remember your calculators? When you plug in a really big or really small number, it comes over the E, which means 10, scientific notation, do you remember that?
Yep.
So like if your calculator said your answer is 1.2 e to the fifth, what that really meant is when your answer is 1, 2, 1, 2, 3, 4. Remember that? So, and I'll show you how to do this, but in your calculators, if you want to go all the way to the left, like this one is asking us to do, this is what you're going to type in. So we're going to use the calculator. So we're going to use a function that's in your calculator called normal CDF. Where you find that is on your calculator, hit the second button, right, the little blue button or whatever at the top left, and then type in the button that says VARS, V-A-R-S. And I think it's the second option, should be normal CDF. Does everybody get that? So, the way this works, and again, the newer calculators list them all out, the older ones you just get to put in comments, and that's okay. So I want you to write down the formula, because I'm sure she's gonna ask you for this next week. The formula is, so on your sheet, you put down the lower bound. So how far left am I going? You put in the upper bound. Then you put in the mean and the standard deviation. And that formula right here will tell us how much of the area we have under the curve. So far, so good. So in your calculators, what you need to put is normal CDF. And I'll explain to you how to find this. So you put in the negative sign, right? Not the minus, but the negative. Now, the way you find the little e is not the alpha E. Hit the second button, now let's forget exactly where it is. Hit the second button and then the comma. Notice in blue, what's above your comma? What does it say? EE, right, little e's. So on your calculator, put a negative, I'm sorry, you need a 1. So put a negative 1, I apologize. Then you go to second, and then hit the comma, and that'll put a little e in there, and be 99.
You're not gonna be doing that, cause you're listening.
What? So then you go to the right. 1.3. This is a standard normal curve. So what is the mean on any standard normal curve? Everybody say 0. 0. And my standard deviation is 1. So type that in your calculator and you're gonna come up with an area. And as you're typing, if you have any questions on how to plug this in,
Press enter.
please let me know. I have no idea what the answer is, so we'll have to do it by group. And I just made up the number. I'm gonna guess it's around 80.8 something.
Point nine.
Okay, 0.9, so I was kinda close. You're good, okay, 0.903, cool. Everybody come up with 0.903.
is he getting his fifth number, or is this thing just gonna assume that I'm
Now,
out?
if your problem goes all the way to the right, guess what? If you go all the way right, you're gonna use one e to the 90. And if you really, just for fun, wanted to do the whole curve, you could go from the left to the right, and what would your answer be? 100%, or point, or just one, exactly. Okay, so, look at the examples, she has some examples on here. So look at the next page, it says find the area between z equals and z equals 0.42. Now what that means on your graph, again, I like to have a cute picture here. It's not real cute, but it works. Maybe 1.45, 0.42, and I want this area.
So with the mean is 0,
Correct.
just make sure.
And whenever, and that's a good question, though. Whenever you're talking about z-scores, you know that your mean is 0 and your standard deviation is 1. Because when you're talking z-scores, you're always talking a standard normal.
So do I have to put the names
So little black, is that option from the other one?
So what did someone come up with for the area under the curve?
It's 0.5892.
5892, I'll go to 4 decimals. 4 is kind of standard, she might want you to go to different ones and different.
I got something different.
Does that make sense so far?
Yes.
So, if you have a standard normal curve and you have z-scores, if you want to find the area under the curve, you just plug in your calculator a normal CDF. Don't ever use the normal PDF, that first one. We're always going to use normal CDF in here. Okay. Now, when she doesn't have it here, but it's kind of fun, what happens? Question. Yes, the reason is, whenever you're looking for an area, you're always looking from the lower or the left-hand side to the right. So on the first problem, I just wanted to go all the way to the left. This one, my lower bound is negative 1.45, so you have to change it in this case. So let's take this exact same problem, and let's say we want to find this area. How would you calculate that area? What's the area under the whole curve? 1. What's the area in the middle? That, right, 0.58?
Subtract 1 from,
Take 1 minus that. So the area in the purple would be 1 minus 0.5892, which may be 0.4108. Sometimes my mental math fails me, but I think that's right. So you can find the area on the outside by taking 1 minus the area on the inside. So far, so good. And I think she has one more fun problem for you to do. Hey, not that one. So look at, look to the next one. It says find the area to the right of z equals negative 0.58. And again, I recommend you draw a picture, draw a graph, a little standard normal curve. So that's what you should get for your four variables.
Yeah, I did it backwards. There we go.
That is a good reminder. So, a couple of things on this one, right? I'm going to the right, so I do 1e to the 99. Second thing is if you ever put them backwards, if I put 1e to the 99 and negative 0.58, you're gonna get a negative area. Right, you always go from left to right, so if you get a negative area, that obviously tells you did something wrong. So what did you come up with on this case? 7190, everybody buy that? Okay. Now, one thing she doesn't even talk about in these notes, at least that I saw, was a z-score. You guys did z-score before, so I wanna mention this. Again, a normal curve can have any mean we want and any standard deviation. But if we wanna convert it to a standard normal curve, remember the z-score, you take whatever value you're talking, your x value, minus the mean over sigma. That ring a bell? So if you get a problem and the mean isn't given, it's not given to be standard normal, and let's pretend your mean was 30 and your standard deviation was 7. So let's take this problem. So if they give you a problem and they say the mean is 30 and the standard deviation is 7, which would be 37, 23. And let's say I want to calculate the area to the left of 35. That's still a normal curve, it's not standard normal. So if I want to calculate the area to the left of 35, first thing, find the z-score. So my z-score would be 35 minus my mean over 7. Then, if I did it this way, I get 5/7. I really need to learn how to think up good numbers up top of my head, which I didn't. So if I take 5/7, what is that? 3 decimals? Now let's go to 2.
7, 1, 4, 2.
So we'll go 7/1. So what that means is I want to calculate the area to the left of 0.71. So if I'm given a different mean and standard deviation, by using the z-score, I can now make it, and now I can do normal CDF. To the left, so it'd be -1 e to the 99, 0.71, 0, and 1. Does that make sense? So I can take a standard, or take a normal curve that has a different mean and standard deviation. I can convert it to a standard normal, and I can still use this. Questions to that? Okay, so she says you got a little bit left in section 6.1, but she is going to save that for you for next week. And what it is if you know the area, how do you go find what the z-score is that matches that? So basically taking these problems and working them backwards. So she's gonna cover that next week. And I'm sure she'll be back by next week, so. I know she was not feeling well yesterday and she went home after her classes, and hopefully she'll be back tomorrow. Any questions? In that case, we get out a little bit early today. If you have any questions, feel free to stay around and ask. Otherwise, thank you very much.